We will start with the webinar. I would like to start with an existing project to show you some basic interface features of the program. So this survey is what we call a pseudo 3D survey. So which means it consists of a number of parallel 2D lines. And here the program workspace is divided into 4 sections. The upper 2 sections are displaying the data, and the lower 2 sections displaying the model. So top right here is a conventional pseudo section. You can switch between the 2D survey lines by using this drop-down list and display the data for these lines. Also, the same as with the 2D version of the program, we can switch to, we can display the data in the form of graphs. Also, we can choose to plot resistances and resistivities. And for the graphs, we can select to group the data based on the size of current dipole, potential dipole, or pseudo depth. Now, top left here is a plan view map of apparent resistivities. So this map is plotted on different depth levels or pseudo depths. And we can switch between these depth levels using this drop-down list here. And currently for this project, we have 25 pseudo depths for which we can plot this plan view map. Another way to display the data in plan view is to plot it in the form of these points. You can choose different sizes for the points. This display mode is very good if you want to show an image on the background. For example, I can upload here a satellite image and like this. And if you want to see some details on the map and display your data simultaneously, this view option is very good for this. Another way to plot the data is to plot pseudo sections in 3D like this. So same as in the 2D version of the program, we can plot observed data or calculated data. Also, we can plot inversion misfits like this. Here, this is the plot of the inversion misfit in the pseudo section. Now, the lower 2 sections here is the model. On the bottom right, we have the slices. So to switch between slices, we can use these toolbar buttons or just use a mouse wheel like this. Those slices can be plotted in 3 different planes. This is currently the XZ plane, and we can select the YZ plane like this. We can go and show the horizontal XY plane like this. Finally, the model here, the 3D model, you can rotate it any way you want. You can zoom in and zoom out on the model. As you can see, you can upload an image. This is currently some seismic section. So for now, I will remove this background. Let me get rid of it. And as you can see, also there are borehole columns plotted in the 3D model. Borehole columns are also displayed in the slices here. There are several ways to visualize your data in 3D. So this way to visualize is called the cross planes, where the data are plotted using 3 orthogonal planes like this. Another way is called a pie cut, where you can just cut this 3D volume in the 3 directions, like so. Next is the inside. Using this option, you can visualize inside of the model. For example, we can set up the transparency for certain resistivity values, thus displaying only certain resistivities that can be considered anomalous, like this. So yes, this is a nice way to render the inner content of the 3D model. Next is called multi-slide, which is basically a set of slices in a selected direction. And finally, we can plot surfaces with constant resistivity values. Here in this program, we can plot surfaces, 3 surfaces simultaneously. We can specify the resistivities, and this is how it will look like with the surfaces. So this was a quick introduction to the program interface. Now we can move on to more practical things. And first, I would like to talk about modeling. Modeling is an important part of geophysics. In the case of ERT, through modeling, we can assess performance of various types of arrays and survey designs, check the resolution and signal levels. So there are 2 options for modeling in the program. The first option is for the ZondRes3D. Here in this dialog box, which is pretty much the same as for the 2D version of the program, we can select the number of electrodes for 2D lines, the separation between them, but also we can, here in this box, we select the number of lines that we want to use and the separation between them. And so also we can set up the measurement protocol here. And let's create this synthetic survey. The next dialog box that appears is a mesh constructor. With synthetic surveys, it's already to use the automatic mesh that the program suggests. We will talk about mesh construction a little bit later today. So for now, I will just apply this. And here we can start modeling. Now, modeling is performed in the 2D section on the model slices. And a good way to visualize your model in 3D is to use the inside mode with the background values transparent like this. And from here, we can just start plotting some objects more or less the same way as as we do in the 2D program, like so. I can copy this model, go to the next slice and paste it, then go to the next slice and paste it. We can switch between the planes. For example, I can now go to the XY plane. I can choose a different form of selection, for example, a rectangular selection, and load it this way. There's also an option to paste the model to all the consecutive slices. This is done like this. Oh, sorry, I forgot to copy that. But yeah, okay. If I copy this and I go to the next one and paste like so. And yes, also we can create layers. Something like this. Like so. So this is how the modeling is performed. Now, after we created the model, we can solve the forward problem. This is done by clicking on this button. For this simple survey design, the process is relatively quick, so we're not going to wait a lot of time here. So, and this is the calculated data for our model. We can go see how different pseudo-depth look like in plane view, and also we can check the pseudo sections. Then if we want to employ a different array type, we can use this option, change array. For example, I want to switch to a dipole-dipole array now and see how this array will perform. I will have to solve the forward problem again for this. And this now is the calculated data for the dipole-dipole array. Also, this model can be exported to a file, and previously saved model can be imported and embedded into this model cube. For example, I will just import another model that was previously created. This is how it looks like. Then another option to create models is to import them from a text file. This text file should contain 4 columns with 3 coordinates of the model cells and the resistivity values. So I will go to the import export. Again, the same option, but here we can choose the XYZD model files, where V stands for the measured resistivity, no, not measured resistivity. And yes, I don't think that one, that was a good one. Yes, here it is a DAT file, but essentially this is just a text file containing 4 columns, coordinates and the resistivity values. So this way you can create some sort of smooth models somewhere, maybe in Excel, and then import these models to the program. Now, this was modeling for the pseudo 3D service, and another option is a full 3D service. 3D modeling can be done in the module called 3D sequencer. This is this module. Here we can create any type of survey design, any complex 3D survey. We start with adding cables. For example, I'll select a cable consisting of 96 electrodes with 5 meters separation between them. And now we can just plot the array position on the map like so. I will go with this kind of snaking array like this. And we can add any amount of cables, and again, as I said, create survey of pretty much any design. After creating the array, we need to add a sequence. For this kind of 3D surveys, bipole array is typically used. We'll have only parallel measurements here, and using this filter box here, we can exclude some measurements that will be prone to high noise levels and lower measured values. So now I'm going to add the sequence. Close to 11,000 data points were added to the sequence. There is a table with the sequence. There is another table with the survey geometry. And also we can visualize the measurement protocol here in the 3D form. This is how it looks like. After that, we can save this protocol, or we can just go to the modeling. This is the mesh constructor again. I'll just go with the automatic mesh. So I want to show the survey points here. So on the 3D model here, the points are, the electrodes are indicated with these points. Now let's do some modeling again. One way to quickly create a model is to go into a 2D mode. And using this mode, we can create some linear 2D objects very quick, like so. I'll just create a couple of these like this, and maybe something like this. So, and we can calculate the forward problem. We can see what kind of signal do we have, the resistivity values. The data displays for this kind of survey, they will be, but they will look weird a little bit. So now if we want to test the inversion algorithm, we can do this operation in the extra submenu. We can choose this command, copy calculated data to measured data. And after that, after clearing the model, we can do the inversion of this data and see how the inversion algorithm will reconstruct our model. So the inversion starts by clicking on this button. Although this is not a large data set, still The 3D inversion takes a lot of time. So I will not be doing a lot of inversion in this webinar. And I will usually stop the inversion after a couple of iterations. So you will see the first inversion results after a couple of iterations. After that, we can just stop the inversion. So we got our first results here. And also this, I think this is a new feature. This window here will plot a graph of a misfit from iteration to iteration to see how the RMS error changes through the process. Okay, well, 2 iterations done. I think I'll just stop this for now. And let's see how this was rendered. Well, could be better, but probably it would get better after a couple more iterations. But this is the basic modeling sequence in ZondRes3D. So let's just move on to other things. Now, the next thing I would like to talk about is data import. When we there's a lot of options for this. First, we can just open files in many different formats, including some manufacturers' formats and also Res3D inf and Res2D inf program format. And one of the good features is the ability to import data from an arbitrary text or Excel file. This is what I'm going to show now. So the text file or Excel file should contain the data in columns. So the data are grouped in columns. For example, in this text file, the first column is the profile number or line number. And now we have to assign all the headers to all the columns. And other columns are coordinates, X and Y coordinates of electrodes and the resistance value, sorry. So now what we're going to do is to assign those headers. That was 2x. And finally, the resistance is this. After clicking OK, the next dialog box is the line selection, but since we specified the line numbers when we were importing, we don't need to do this. This is automatic. So we go again to the mesh constructor, and now we have our data imported like this. Another common case when we want to create a 3D project is to open several 2D lines. Now I have 13 lines here. These are 13 2D lines. These are stored in the Res2D inf format. So I select all 13 of them and click open, and the program suggests to create a 3D project from multiple 2D lines here. And for this, we need to assign the coordinates for each of these lines. Apparently, X coordinates were already assigned in the files, so we just need to assign the Y coordinates. So I know these lines are spaced 1 meter apart. So I'm just going to specify those y coordinates for all 13 of these lines. Okay, done. And again, the line selection, which is already done automatically. And now we have imported 13 2D lines and created the 3D project from this data. One common question that is frequently asked is, can we process 2D data in this program, in the 3D version? And the answer is yes, we can do this, but this comes at a price, because the three-dimensional program doesn't have that many options that the two-dimensional program has. Because many options, it's quite easy to realize in the 2D version, but it's not easy to realize in the 3D version. So not so many options here as compared to the 2D version, and also the inversion process in the 3D version is a few times slower than in the 2D. I will just open one file to demonstrate. This is just one single line here, a 2D survey. And in the mesh constructor, the program automatically selects one line for the mesh type. This is the mesh for 2D. And this is basically how it looks like. Let's just run a quick inversion on this. And so for processing of 2D lines, what we basically have here is just a 2D model in the 3D cube, like this. So let's talk about mesh construction in more detail, because mesh is very important for 3D. It affects a lot of things, including forward problem solution and inverse problem solution. So now I will open another project. And let's go to the mesh constructor module. So first, there is an automatic mesh construction. You can use, you can choose between several mesh types. Basically, it's regular and general. I guess they're more or less the same. General means more generalized version of the regular mesh. So the problem with this is that the point of this grid mesh is that we need our electrodes to be at the intersection of the grid lines. But as you can see, some of the electrodes are in the nodes, but many electrodes one option, there's also try to build this manual mesh. There's also an option to add grid lines manually or remove those grid lines like this. But for any type, pretty much any type of real-life surveys, when you have real coordinates and topography, we recommend to use a mesh which is called a trapezoidal mesh. So for this, there's another module for creating a trapezoidal mesh. I will just go through this module very quick. So these are locations of our electrodes, and first thing we need to do is to specify the lines. This can be done using a couple of tools. So you can use this manual tool. Also, if these lines are parallel, then we can use an automatic line selection by clicking on this button here. For a set of parallel lines, this will work pretty well. So you can see that all the lines are now color-coded. And now we can create these lines. And now the only thing we need to do is to set a line. One line is enough in the another direction, perpendicular direction. I can do it like this and then just create this grid like so. If needed, we can correct the alignment doing like this, but here it's not really needed. So now let's go back to the mesh constructor. And now you can see that with this trapezoidal mesh, all our electrodes are at the node locations, like perfectly at the intersections with the of the grid lines. Two options here for the mesh. First, we can position the electrodes at the intersections, as I just did. This option is used for the total potential calculations. And another one is secondary potential calculation, for which we position the electrodes within the cells. And this option is considered more accurate, and it also allows removing the source singularity. Another thing in the mesh constructor is you can visualize this mesh in 3D, like so. Sometimes when the topographic data are collected using a few points, there's a necessity to smooth the topography. This can be done using this option. We can set a topography smoothness coefficient and rebuild the mesh. Oops. And the topography will be smoothed with this option. So, and talking about topography and coordinates in general, very often, if not always, we don't have the absolute coordinates or topographic data in our data file. So usually the data files only consist the relative coordinates, cable lengths, and no topography. And so the program has an option to import coordinates and the topographic data. Let me open another project to demonstrate this. Now, this is a survey consisting of 8 parallel lines. Apparently 1 meter spacing between electrodes, 1 meter spacing between the lines. So definitely this is a relative coordinate system. So what we can do now, if you go to the mesh construction module, there's a set of options for coordinates and topography. So first thing we can do, we can invert coordinates from a text file. So this text file, again, it consists of columns containing references to all the electrodes and then respective coordinates and topographic data. So now we import this coordinates. This is how our coordinates system looks like now. And also there's an option to display the topography on a map. As you can see, this the coordinate text file that we imported already had some topography there. There is an option to remove the topography. So the topography is removed. We now have this flat surface, and finally we can import the topography from a separate file. Again, this file is a text file with columns of references to the electrodes and topographic data. And so now we can display the new topography. Go to the 3D display. This is a new topography from a text file. Another example, let me open another project here. So now this project, again, it's a pseudo 3D, number of 2D lines combined. Let's just set the opacity, and you can see here we have the cutting applied to the model. We can do this using this cutting submenu. We can specify the cut angle. For example, I will cut it at, say, 25 degrees angle, like this. Also, in this submenu, there is an option to display only a portion of the model by creating a polygon like this. And in this way, you can only display some portion of the model within the polygon boundaries, like so. Of other features here in the 3D, we can upload a satellite map, an image, using Bing Maps. For this, you need the UTM coordinates, and you need the specific UTM zone. And so the program will search in the internet and upload this satellite Bing image to the model. Now let's talk a little bit about the data processing when we import the data. So one of the options here is when we import some data, we can apply the data filter. So this is done by selecting this option. After that, when we open a file, this dialog box appears where you can filter your data based on geographic coordinates based on the survey geometry and also on the resistivity values. For example, here, this survey, apparently it's very noisy, some unrealistic resistivity values here, so we can specify some more realistic values for resistivities and filter the data this way. Now, next option will be to remove unstable records. So unstable records mean those data points for which measured values can change significantly with slight changes in geometry. So this is the plot of the data points based on the various geometric factors. And as we can see, these data points are basically outliers. There's huge misfit values here, and we can set the cutoff level. Automatically it's set to 10%, but we can probably to 10, but we can probably choose a lower value, maybe 8. And this way we removed 608 records from the data set that the program will consider unstable or noisy records. And another option for the data processing is the same quality control module as used with the 2D version of the program. I'll just open this other 2D line again, and I need the filter, and let's have a look at the quality control module real quick, because we covered this in more detail in the webinar on the 2D version. So here in the quality control module, we can see what kind of array is used for the survey. You can display the graphs grouped based on various parameters. And finally, we can go through all the graphs and remove points that we consider to be noisy. Like, for example, these 2 points probably outliers. We don't like them. And this way we're just going through the whole data set and removing those noisy points. And after that, we can delete those points and go perform the inversion. And finally, there is the last option for data processing that I wanted to show is the post-inversion removal of noisy measurements. I will just stop the inversion for now. So there is in the extra subsection this remove data with large misfits option. It brings up this dialog box where the misfit is plotted based on geometric factors, and you can see the distribution, and you can set the cutoff level like this, and so these are apparently outliers that can be removed using this dialog box. So we just removed 239 data points from the data set. And now, finally, I will open a project and perform an inversion on the model. So this again is a synthetic model. This is a piecewise smooth, this is a piecewise constant model. So in the inversion parameters, two good options for this kind of model will be focused inversion, or we can use Occam inversion with a robust smoothness algorithm. Another good option here in the program setup is cell grouping. So this is basically, this is not a large data set, and it doesn't require a lot of resources from your computer. But when you deal with huge data sets, this can become critical. And when we perform the cell grouping, first thing here at the status bar, you can see that for inversion, we need to define 8,400 parameters, and we need 200 megabytes for solving a forward problem and 100 megabytes for inversion. And it also shows you the available amount of memory. So this is not critical test, so it can be performed like this, but sometimes, as again, large projects require a lot of computer memory. So this is why we use cell grouping. It is basically, this is a good practice to apply the cell grouping regardless of the amount of memory, because the natural resolution of the meta decreases significantly with depth. So this will only makes it good for the inversion. So I just grouped some cells. Now we can see that we need to define 3,600 parameters and only 50 megabytes of memory needed for this, for the inversion. Okay, before running the inversion, I will clear this model. And also this model is already saved into the buffer, so later we can compare the result with the original model. So clear the model, and now we can start the inversion process. Again, I will not be waiting for 10 iterations. I'll stop it a bit earlier, but we'll have a good idea of the inversion result after a couple of iterations, maybe 4 or 5. And yes, again, this window here displays the progress of the RMS error with each iteration. Okay, I'll probably stop it now. And so to see what we got here, we will go to the inside mode, and we will apply some transparency to background values so that we can render the anomalous 3D objects. Okay. Like so. Okay, so this is the inversion result. So the location of the anomalies is pretty much correct. The resistivities are probably a bit off. Now we can go back to the original model and request it back from the buffer and see what's the difference between the inversion model and the original model. You can see that's what's the difference here. Now I'm going to show a couple of interesting projects. Now the first one is a project containing a cross-hole survey. So this project is stored in the ZondRes3D inv program file. I need to switch off that filter. So yes, the program asks us to confirm that there is a borehole survey. So here is the survey grid, and as you can see, this project has both ground electrodes on the surface of the ground and borehole electrodes. There are four boreholes here. So this type of projects, combined borehole and ground service, can be processed and interpreted in ZondRes3D. Another project is a marine survey. So this survey was conducted with electrodes positioned on the bottom, at the bottom of an aquatic body. So for the 3D model, the program shows the bottom topography, but here on the vertical slices, this blue color indicates the water. So we can specify a couple of parameters for the aquatic surveys, like water resistivity, and add some additional subdivisions layering in the water. So this is for the marine surveys. And finally, one other project is a project that was the survey that was conducted using this square array. So apparently, this survey was conducted around this building here. So it's a square array along the sides of the building. And as you can see, we were able to get some resistivity values underneath this building. And it appears to be a good model. So I think, and yes, I think I'm done with the presentation pretty much. Just a few words about exporting your results. So there is one option that can be employed is you can create a video of the 3D model using this command. So this 3D model rotates like this, and by clicking on this button, you can start the recording. And when you stop the recording, a video file will be saved on your computer with this animation, this 3D section here. And also all the planes and 3D surfaces, they can be plotted directly in Golden Software Surfer and Voxler programs. I do not have neither, I have neither of these programs, so I think I will stop my presentation for now. And if Alex wants to show you how this can be done, the expert to Surfer and Voxler, I'll pass the microphone to him. Alex?
Thank you very much, Ilia. It was great to hear your presentation. I will try to show you some extra possibilities of software before we start the question sections. So we missed exporting to this softwares mentioned by Ilia. Oh, sorry. Can you see my screen?
Not yet. Yes, we now can see a screen.
Okay, good. This is the same project Ilia showed. Just one. So we have three basic options for exporting models. The different professional software like Voxler, Golden Software, Voxler, Surfer, and ParaView. So of course you can use exporting grid files because they can used in RockWorks and the same project. But for fast exporting is much better to use something like Voxler. So I just show you because you don't need to do something, it's will done automatically with these options. For this model you can see on the screen. And I just create script file and it's automatically opened by Voxler. Of course, it takes some time because this is a big grid. Okay, it's done. Now we have our model exported to the Voxler. Of course, it's not all. We can do it with isosurface. For example, I'll build two isosurface and we'll try to also export it to the Voxler. Again, let's take some time. Let's see what we have. Yes, we have two isosurface in Voxler now. Okay. For exporting to the surfer, we need to specify depths of slices. It suggests 3. It's equally divided from minimal to maximum depth from the surface, or it can be just planes on the some absolute depths, not here options from surface. And I can build it, I can change it, I can make more, and here is resolution of output grid. It's all building automatically. And now here this 3 slices. Of course, we can zoom it and do something else. Okay, and last option for export is ParaView, but it's only create a file. I don't know a lot about ParaView now because I just started to work with this software. Maybe after we can do automation for this export. Okay, and a couple of extra options which were added very recently. And first one is a priori boundaries if they need. For example, open some file. If I need, because I see here is a generally 3-layer model, one high resistivity layer, and I need to have sharp boundaries. I would add these a priori boundaries, and it is in inversion, that a priori boundaries. And here I can create arbitrary shape of boundaries or all plane. For example, I should choose slice here. And this will be cutting boundary. For contrast, or I can use full. Okay, because I have one layer, I would have 2 boundaries. You can see it right here. And now I can make inversion with taking account these 2 boundaries a priori. Just a few iterations because this problem is already medium size. So it's not so quick, especially for my computer. And you already see the difference. We have a sharp boundaries in this model. So it looks much better. I think 3 iterations will be enough. Okay, I'll stop it. So here is quite good layers with sharp boundaries. Okay, and one more options which was taken from a 2D version of software is data editor. Here you can select measurements for resistivity or for IP if we switch to IP mode. And also it shows us position, electrodes position, if we change row here, or otherwise we can select measurement on pseudo section and it will be selected in this table. Also, you can see in IP mode, you can see if you have time domain data, IP decays instead of values. So it's maybe useful sometimes to see the data in the table. Of course, all sorting options is available. And okay, here we go with your questions.
So yes, I see there is no question in the chat, and I'm going to ask everyone to unmute. And if any of you have questions, then you can unmute yourself and ask them.
I just have a quick question. You were a bit fast with the clickings and all that. So I was wondering if there is a place where we could get a recording of this webinar.
Oh yes, this webinar was recorded, but unfortunately I've seen the recording stopped like midway, and then in a few seconds it started again. So there might be 2 files, I mean 2 videos for this webinar, but Alex typically posts those recordings in his YouTube channel, and also there will be a post in LinkedIn with the recording.
Okay, thank you.
No problem. You're welcome.
It was a technical problem, I don't know, but fortunately Zoom recover all automatically very soon. I don't know what happened. Here we have one question in the chat box about using of vertical electrical sounding data in this software as 2D input to perform 3D inversion. Yes, there is no limitation on electrodes position in software. So it could be VES, it could be tomography. But you know, VES used to have a very small spacings for central point, and to model it, to model several VES points, you need very dense mesh, and this means a lot of resources. So if you have, for example, 100 VES point on your site, it should be very, very dense point, and it will be maybe 4-5 gigabytes of memory just for a forward solver, and maybe a little less for inverse solver. So it will be, it's possible, but I think ERT much better for 3D. Okay, we have no more questions, but if you have any question, please ask. Okay.
Yes, and yes, I just posted the link for the Alex's YouTube channel if everyone is interested. So in the chat, there is a link to the YouTube channel.
One more comment, sorry, Ilya. Because this presentation is only 1 hour, we couldn't discuss all function in details. But as Ilya correctly said, you can find all information on our YouTube channel, because there is a lot of video, and every video is dedicated to 1 or 2 function. So all clicks, all key pressed is fixed and described in these videos. There is no sound, but there is text comments in most videos.
Okay, excuse me. I want to ask a question.
Yes, go ahead, please.
Okay. It's very nice website in this night. And excuse me, I want to know, these days I'm build a ocean model use this software, and how to set the water on the top of the model.
This is very simple. If you need to set just a simple water layer, you can use topography section of your data file, and instead topo word, you use topo plus W word, and add 3 parameters: water resistivity, water level, it's used to 0, and number of subdivision. The same like you see in main menu options. In this case, all your electrodes will be on the bottom of sea or lake. In case you need underwater survey, you should use another key. So it should be star, topo plus W plus star. You can see all these examples in a software zip file for different way of water settings. Also, you can change it automatically in software, or you can use ZondRes3D in files, and if water layer is set it up in these files, it will be interpreted correctly.
Okay, thank you very much. But
So I just wanted to add to Alex's explanation that there's a topic that we haven't discussed at all because of the time limitation. And he was basically talking about importing your data using a random arbitrary text files, where all the data is contained in columns. And in the end of this file, you can add either topographic information, or you can add the information regarding the water levels and water resistivities. And yes, we haven't covered this, but in the program manual, there is a section dedicated to this topic. And as far as I understand, Alex said that in the program package, there are some text file examples with this.
okay, thank you very much.
Thank you for your question. And we have two more questions. First one about next webinar, which ask it to be dedicated of gravity modeling. So it's gravity magnetic modeling. Yes, we planning this webinar, but not this or next month, maybe after. Yes. And question about vertical electrical soundings. Yes, I see your question. That you have 80 VES points with average spacing 1 kilometer between. No, you couldn't do a 3D inversion for very big spacings between soundings. The same thing for ERT. If you have a very long distance between lines, it's became not 3D, it became 2D. So no, you should have distance between points, I think minimum one, no, maximum 1 and 1/4 of maximal spacing. So it's not good. You can do it in software, but it's not not good. It's not ERT and it's not a 3D. So it's just separate point. One more question. You have a discounts for students. Yes, we have discounts for universities. If university purchase from us, yes, we provide discounts.
Well, if there are no other questions, I think we will wind up with this webinar. Thank you everyone for attending, and thank you for your questions, and I hope we will see you next time.